Hello, our group, Team Thermos, comprised of myself, Michelle, Chris, John, and David, are working on a project to compete with the cost and effectiveness of photovoltaic solar energy. Our idea uses the thermal gradient between a sun-heated black body and below ground temperature to drive a small steam power turbine.
A simple observation of extremely hot asphalt in the southwest United States and some background knowledge on thermal power plants, specifically low thermal gradient power plants, such as ocean thermal and geothermal, inspired this idea. Due to recent natural disasters and rolling blackouts, this became an idea that was easy for us as a group to rally behind. Although our backgrounds vary, we all understand the importance of renewable distributed energy resources.
Our market research has shown that the vast majority of Americans are wishing for a stronger presence of renewable energy in power generation. Out of 134 respondents, the average importance of renewable energy was ranked an 8.5 on a scale of 1 to 10. And it isn't just our own market research. Years of Gallup polls and Consumer Report surveys show that Americans would like to see an increase in renewable energy. 79% of our survey participants who don't have distributed generation said that the cost was the main factor preventing them from investing in renewables. This isn't a surprise. The Union of Concerned Scientists has called the large upfront capital cost the most obvious and widely publicized barrier to renewable energy.
Our design for a solar thermal renewable energy source involves three main subsystems: an evaporator, a core plant, and a condenser. Due to the time and financial constraints of this course, we've limited the scope of our design primarily centered around the evaporator. We intend to build out the evaporator and simulate the plant and condenser systems using Simulink models and other software such as EcoSim that have an organic Rankine cycle toolkit and a solar thermal simulation capability. With this simulation, we're also going to test the scalability of our design. We would like to engineer a design that could work both in a residential or commercial scale, like on a rooftop or a long stretch of highway.
To date, we have wrapped up our initial market research survey and are currently using a sensor that Chris designed to collect local data on solar radiance and ambient temperature in Southern California. We will be deploying these same sensors to the locations of the other team members to gauge the best geographic regions for system use.
Our next step will be working on the design for the plant and feedback systems. We plan on using the simulation to determine the most efficient working fluid and thermal range. Using the simulated data, we will be able to design and manage the flow control systems of the fluid in the evaporator. We will also be testing and researching various materials for collector efficiency. With all the data collected, we will then build and test a 1.6 square meter prototype to compare against a 1.6 square meter photovoltaic panel. Thank you.